Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us deep within the Earth, to the majestic world of volcanoes. We will drift tonight through landscapes of fire and shadow, exploring the quiet, immense power that sleeps beneath the crust of our world. These great mountains are not merely features of rock. They are the Earth's own voice, speaking in ancient tongues of steam and stone. They are the architects of new lands, the sculptors of islands, and the faithful guardians of the deep, hidden warmth that pulses far below our feet. We will listen to their stories, not stories of sudden anger, but of slow, patient creation, of pressure building over millennia, of continents breathing, and of the planet itself constantly, quietly remaking its own surface in a cycle as old as time. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. The largest active volcano on Earth is Mauna Loa in Hawaii. This colossus is not a sharply pointed peak born of violent explosions, but a gentle giant, a classic shield volcano, built by the patient accumulation of countless lava flows over hundreds of thousands of years. It rises from the deep ocean floor, its true height hidden by the Pacific Ocean, reaching an elevation of over 13,600 feet, or about 4,170 meters above sea level. But its base is far deeper, making its total height from the seabed greater than that of Mount Everest. Mauna Loa's slopes are broad and gradual, a testament to the fluid, basaltic lava that travels long distances before cooling. Its name means long mountain in Hawaiian, a simple and fitting description for a structure so vast it has shaped the island itself, its immense weight actually depressing the oceanic crust beneath it. This mountain is a quiet engine of creation, a place where the Earth's mantle speaks directly to the surface, reminding us that the ground beneath us is not static, but a living, breathing, and ever-growing surface. Many of the world's most iconic mountains, like Mount Fuji in Japan or Mount Rainier in the United States, are stratovolcanoes. These are the mountains of postcards and paintings, their symmetrical, cone-like shapes climbing gracefully into the sky, often capped with snow and ice. Unlike their shield-shaped cousins, stratovolcanoes, also known as composite volcanoes, are built from layers of hardened lava, ash, tephra, and pumice, all stacked one upon the other like geological masonry. This layering tells a story of a more varied and often more dramatic life, a cycle of explosive eruptions that send ash plumes high into the atmosphere, followed by periods of quieter lava flows that bind the loose material together. This alternating history creates their steep signature profiles, but it also harbors a deep instability, making them capable of great, sudden transformations. They stand as monuments of geologic tension, beautiful and serene from a distance, yet holding within their layered hearts the restless energy of the planet. Cinder cone volcanoes are one of the simplest and most common types of volcanoes found across the globe. They are not the towering giants of legend, but often appear as steep, conical hills, sometimes rising only a few hundred feet, or perhaps 100 meters, although some can grow larger, reaching over 1,000 feet, or more than 300 meters in height. They are born from a single, typically short-lived eruptive episode, where gas-charged lava is blown violently into the air from a single vent. This fiery spray cools and solidifies into cinders, or scoria, which fall back to Earth, building up a circular or oval cone around the vent, like sand piling up in an hourglass, A famous example is pyroclastic, which famously grew from a cornfield in Mexico in 1943, offering humans a rare chance to witness the birth of a volcano from its very first breath. These modest cones are the Earth's geological punctuation marks, small, sudden, and scattered reminders of the molten world just waiting beneath the surface. Viscous, sticky lava can create a formation known as a lava dome. When magma rises to the surface, its behavior is dictated by its chemistry, particularly its silica content, which governs its viscosity or its resistance to flow. While fluid, low silica lava spreads far and wide to build shield volcanoes, magma that is thick and pasty, rich in silica, does not travel easily. It slowly extrudes from a vent, and unable to flow away, it piles up directly over the vent, creating a steep-sided mound-shaped protrusion. These domes often form within the craters of larger stratovolcanoes after an eruption, like a plug in a drain. The lava dome that grew inside the crater of Mount St. Helens after its 1980 eruption is a classic example. Because they act as a cap, they can trap gas beneath them, leading to immense pressure buildup that can result in sudden, dangerous explosions, making these quiet, slow-growing mounds some of the most unpredictable features in volcanology. A caldera is a massive, cauldron-like depression formed when a volcano collapses into itself. These are not the craters of typical eruptions. They are the immense scars left behind by the most powerful volcanic events on Earth, known as super eruptions. Such an event begins when a colossal magma chamber, a subterranean reservoir of molten rock, empties so completely and rapidly that the ground above it, the volcano's own edifice, loses its foundation. The overlying rock, lacking support, collapses downwards into the now voided chamber, creating a vast circular basin that can be many miles or kilometers wide and thousands of feet deep. Yellowstone National Park in the United States is one of the most famous examples. Its geysers and hot springs all bubbling within a giant caldera, left by an ancient eruption of unimaginable scale. These massive depressions are quiet now, often filled with water to form deep lakes, like Crater Lake in Oregon. But they remain as serene, sleeping reminders of the planet's most profound and transformative power. The distinction between magma and lava is a matter of location. Deep within the Earth, molten rock exists in chambers under immense pressure and high temperatures, where it remains a fluid, mobile substance we call magma. This magma is a complex brew of molten silicate minerals, dissolved gases, and sometimes suspended crystals, all waiting for a path to the surface. It is the lifeblood of the volcano, the fuel for its fire. When this magma finds a conduit, a fissure or a vent, and erupts onto the Earth's surface, it loses its cloak of pressure, and the dissolved gases within it begin to escape. At this moment of its arrival, emerging into the air or the sea, this same molten rock is renamed lava. Lava is magma that has seen the sky, magma that has begun its final journey of cooling and solidifying into new rock, new land. It is a simple change in name, but it marks the transition from the hidden potential energy of the deep Earth to the kinetic, creative, and landscape-altering force on the surface. The vast majority of the world's volcanoes are located in a region known as the Pacific Ring of Fire. This immense, horseshoe-shaped path stretches for about 25,000 miles, or roughly 40,000 kilometers, encircling the basin of the Pacific Ocean. It is not a ring of fire in the literal sense, but a ring of intense geological activity, marking the boundaries where the enormous Pacific tectonic plate grinds against and dives beneath other major plates, such as the North American, South American, and Eurasian plates. This process, known as subduction, is the engine that drives the ring of fire. As one plate sinks into the mantle, it heats up, releasing water that causes the overlying mantle rock to melt, creating the magma that feeds the hundreds of volcanoes that dot this zone, from the Andes in South America to the Cascades in North America, and across the ocean to Japan and New Zealand. This ring is a testament to our planet's dynamism, a place where the edges of continents are forged and reforged in a constant, slow-motion collision. The behavior of lava is governed by its viscosity, which is its resistance to flow. This property is primarily controlled by the lava's temperature and, most importantly, its chemical composition, specifically its silica content, magma, with low silica content, like the basaltic lavas found in Hawaii, is very fluid and flows easily, much like warm honey. This low viscosity allows it to spread across the land in vast, thin sheets, traveling for many miles or kilometers and building up the gentle slopes of shield volcanoes. Conversely, magma with a high silica content, such as rhyolitic magma, is extremely thick and sticky or viscous. It flows slowly, like cold toothpaste, piling up and creating steep-sided lava domes, or, if it traps enough gas, powering highly explosive eruptions. This single chemical difference, the amount of silica in the molten rock, dictates the entire personality of a volcano, from its shape and size to the nature of its eruption, determining whether it will be a quiet builder of land or an explosive shaper of landscapes. Hawaiian volcanology gives us the beautiful, descriptive term pahoehoe for a specific type of lava flow. Pahoehoe, which means ropey in Hawaiian, describes lava that is very fluid, typically basaltic, and low in viscosity. As this hot, fluid lava flows across the surface, its outermost layer begins to cool and solidify upon contact with the air, forming a flexible, skin-like crust. The molten lava beneath this skin continues to move, dragging and wrinkling the surface crust into a series of smooth, billowy, or ropey textures that look like coiled ropes or folds of satin fabric. It is a gentle-looking flow, a river of rock that appears soft and malleable, even as it burns with intense heat. This type of lava flow advances relatively slowly, allowing the insulating skin to form, and it is a hallmark of the non-explosive effusive eruptions that build the great shield volcanoes, a beautiful and mesmerizing display of new Earth being born. In stark contrast to the smooth, ropey surface of Pahoehoe is the form of lava known as AA. This Hawaiian term, pronounced AA, perfectly captures the experience one might have trying to walk across its surface barefoot. AA lava forms from a similar basaltic magma, but it is typically cooler, more viscous, or flowing at a faster rate, which causes the cooling crust to tear apart rather than fold. As the flow moves, this brittle, solidified crust on the surface breaks into a chaotic jumble of sharp, jagged, and spiny fragments, known as clinker. This clinkery, rough surface is then carried along by the molten, pasty core of the flow, much like a conveyor belt. The sound of an advancing AA flow is a distinctive one, a grinding, crackling, and crunching noise as the clinker tumbles down the steep front of the flow. It is the harsher, more chaotic face of lava, leaving behind a field of forbidding, rough terrain that is a challenge to traverse, a stark monument of cooled, shattered rock. When lava erupts underwater, it creates a unique and fascinating formation known as pillow lava. This process occurs at mid-ocean ridges, the seams of the planet where new oceanic crust is born, as well as when surface lava flows from a coastal volcano, like Kilauea in Hawaii, finally meet the sea. As the molten rock, which can be over 1,000 degrees Celsius, or nearly 2,000 degrees Fahrenheit, pushes into the cold ocean water, its outer surface is instantly quenched, flash cooling to form a glassy solid crust. The lava inside, however, remains molten and continues to push, inflating this crust like a water balloon. This pressure eventually causes the pillow to rupture, and a new lobe of lava emerges to repeat the process, budding off from the first. This cycle of budding and quenching, over and over, creates an accumulation of interconnected, rounded, pillow-shaped structures that, when seen in ancient rock formations, are a clear signature that the rock was born beneath the waves, a silent testament to an ancient submarine eruption. Volcanic ash is not the soft, fluffy residue of burned organic material, but is instead a harsh abrasive material composed of pulverized rock, minerals, and volcanic glass. It is created during explosive volcanic eruptions, when the violent expansion of hot gases shatters the magma and the surrounding solid rock into tiny, jagged particles. These particles are defined by their size being less than 2 millimeters, or about 0.08 inches in diameter. Anything smaller than a grain of sand. Despite its name, this ash is cold and hard when it falls from the sky, often miles or even hundreds of miles from the volcano. Its microscopic, sharp-edged structure makes it a significant hazard. It is heavy when wet, capable of collapsing roofs, and dangerous to inhale, as the glassy shards can damage lungs. It can also disrupt air travel by scouring jet engines, and yet, over the very long term, this same destructive material weathers and breaks down, contributing to the formation of incredibly fertile soils, breathing new life into the land it once covered. A pyroclastic flow is one of the most devastating and formidable phenomena associated with a volcano. This is not a flow of liquid lava, but a fast-moving, ground-hugging avalanche of hot gas, ash, and heavier volcanic debris, known as tephra. These flows are born from the collapse of an eruption column, or the spilling over of hot material from a vent, and they can race down the flanks of a volcano at terrifying speeds, often exceeding 50 miles per hour, or 80 kilometers per hour, and in some cases reaching several hundred miles per hour. The temperatures within these clouds are extreme, typically ranging from 200 to 700 degrees Celsius, or about 400 to 1,300 degrees Fahrenheit, instantly incinerating everything in their path. They are a chaotic, turbulent mixture, where the solid particles are suspended by the expanding hot gases, allowing the flow to move almost frictionlessly across the terrain, filling valleys and sweeping over ridges, a truly awesome and destructive expression of the volcano's explosive power. A lahar is a volcanic mudflow, a destructive force that can travel far beyond the immediate vicinity of a volcano. These flows are a dense, concrete-like slurry of water, mud, rock, and volcanic debris, and they can be triggered by several mechanisms. A large eruption can rapidly melt snow and ice on a volcano summit, as happened tragically at Nevado del Ruiz in Colombia in 1985. Heavy rainfall on slopes covered in loose, unstable volcanic ash from a recent eruption can also mobilize the material, creating a lahar. They can even occur long after an eruption has ceased. Once in motion, lahars follow the path of least resistance, surging into river valleys and sweeping downstream at high speeds, capable of burying entire towns and reshaping the landscape. They are a powerful reminder that a volcano's influence does not end with its eruption, but that its deposits, the ash and rock, can be reawakened by water, carrying the mountain's legacy downstream long after the initial fire has cooled. The eruption of a volcano releases more than just lava and ash. It also emits a vast cocktail of gases, which can create a phenomenon known as VOG, or volcanic smog. The primary gases released are water vapor, carbon dioxide, and sulfur dioxide. When sulfur dioxide, a pungent gas, is released into the atmosphere, it reacts with oxygen, sunlight, moisture, and other particles to form fine, acidic aerosols, or tiny liquid droplets. This creates a hazy, yellowish-brown smog that can be carried by the wind for hundreds of miles. VOG is a persistent feature around constantly erupting volcanoes like Kilauea in Hawaii, where it can cause respiratory irritation, damage crops, and reduce visibility. It is a quiet, airborne reminder of the volcano's constant activity, a chemical breath that drifts on the breeze, subtly altering the air and reminding those nearby of the active, living geology just beneath their feet. The single largest volcano on Earth is Tamu Massif, a truly colossal shield volcano submerged deep in the northwestern Pacific Ocean. For a long time, this immense feature was thought to be a collection of separate volcanoes or a broad oceanic plateau, but research has revealed it to be a single massive entity. Tamu Massif covers an area of about 120,000 square miles, or 310,000 square kilometers, making it comparable in size to the state of New Mexico or the British Isles. Unlike the tall, conical volcanoes we picture on land, it has incredibly low, broad slopes, rising about 2.5 miles, or 4 kilometers, from the seafloor. But over a vast, vast distance, it was formed around 145 million years ago by the eruption of incredibly fluid basaltic lava that flowed for immense distances. Today, Tamu Massif lies dormant, its fires cooled, a silent, sprawling giant resting on the ocean floor, its sheer scale a testament to a period of profound volcanic activity in our planet's past. While Mauna Loa is the most massive active volcano, its neighbor, Mauna Kea, also in Hawaii, holds the title of the tallest mountain on Earth when measured from its base to its peak. Like Mauna Loa, Mauna Kea is a dormant shield volcano that rises from the deep Pacific seafloor. Its summit reaches an elevation of 13,803 feet, or 4,207 meters, above sea level, which is slightly higher than Mauna Loa's. However, when you measure its full height from its base, which is submerged more than 19,000 feet, or nearly 6,000 meters, below the ocean surface, its total stature is over 33,000 feet, or more than 10,000 meters. This is significantly taller than Mount Everest, which, while having the highest elevation above sea level, rises from the already high Tibetan Plateau. Mauna Kea is a sacred mountain in Hawaiian culture, its summit so high that it pierces the clouds, a place where the air is thin and the stars are brilliant, a true bridge between the deep ocean and the cosmos. The largest known volcano in our solar system is not on Earth, but on the planet Mars. This colossal shield volcano is named Olympus Mons, and it dwarfs any feature on our own world. Olympus Mons stands at a staggering height of nearly 14 miles, or 22 kilometers, which is almost 3 times the height of Mount Everest above sea level. Its base is so vast, stretching about 374 miles, or 600 kilometers across, that if you were standing on its summit, its slopes would extend beyond the horizon. The entire state of Arizona could comfortably fit within its footprint. The volcano's immense size is attributed to Mars's lower surface gravity and its lack of tectonic plates. On Earth, tectonic plates move over hotspots, creating chains of volcanoes like Hawaii. On Mars, with no plate movement, the crust remains stationary over a magma hotspot for eons, allowing Olympus Mons to grow undisturbed, layer upon patient layer, into the solar system's most majestic and monumental mountain. Volcanoes are not limited to a world of rock and fire. They also exist in icy forms in the cold, outer reaches of the solar system. These are known as cryovolcanos, or ice volcanoes, and they have been observed on moons like Neptune's Triton and Saturn's Enceladus. Instead of erupting molten rock, these fascinating features erupt cryomagma, a slurry of volatile substances such as water ice, ammonia, and methane, which are liquid in the deep, warmer interiors of these moons, but frozen solid on their surfaces. The eruptions are driven by internal heat and pressure, sending plumes of these icy materials and gases high into the thin atmospheres, or even into space. The geysers of Enceladus, for example, spray jets of water ice particles far from its south pole, feeding one of Saturn's rings. These cryovolcanoes are a beautiful reminder that the fundamental processes of geology, heat, pressure, and the movement of material can express themselves in profoundly different ways, painting landscapes of ice instead of stone. A supervolcano is not a specific type of volcano, but rather a term for a volcano capable of producing an eruption of unimaginable scale. These eruptions are defined as those that eject a volume of material greater than 240 cubic miles, or 1,000 cubic kilometers, which is thousands of times larger than typical volcanic eruptions. A super eruption doesn't come from a conical mountain, but from a massive, often hidden caldera, the remnant of a previous collapse. The magma chamber beneath is so vast that when it finally erupts, it does so with planet-altering force, capable of blanketing entire continents in ash and releasing enough gas to significantly alter the global climate for years. Locations like Yellowstone in the United States, Lake Toba in Indonesia, and Taupo in New Zealand are all sites of these ancient, colossal events. They are not waiting to explode, but rather represent the slow, patient breathing of the Earth's deep mantle, operating on a timescale so vast it humbles our human experience, reminding us of the immense power sleeping quietly beneath the crust. The 1980 eruption of Mount St. Helens in Washington state was a profound lesson in volcanic power and transformation. For months, the mountain had been stirring, signaled by earthquakes and a growing visible bulge on its north flank, a sign of magma pushing relentlessly from within. Then, on the morning of May 18th, a large earthquake triggered the collapse of this oversteepened north face, which became the largest debris avalanche in recorded history. This massive landslide uncorked the pressurized magma chamber in a unique and devastating way, unleashing a lateral blast, a sideways explosion of hot gas, ash, and rock that surged outwards at speeds exceeding 300 miles per hour, or nearly 500 kilometers per hour. This blast scoured the landscape for 230 square miles, or about 600 square kilometers, leveling forests and instantly changing the world from a lush green to a muted grey ash. The event was a powerful reminder that volcanoes do not always erupt straight up, and that their energy can be directed with an awesome, landscape-altering force that reshapes the world in mere moments. The 1883 eruption of Krakatoa, an island volcano in the Sunda Strait between Java and Sumatra, was one of the most catastrophic events in modern history. The eruption was not a single bang, but a series of 4 colossal explosions on August 27th, so powerful they were heard thousands of miles away, in places as distant as Perth, Australia, and the island of Rodriguez near Africa, over 3,000 miles, or nearly 5,000 kilometers, distant. The explosions and the subsequent collapse of the volcano into the sea generated towering tsunamis that radiated outwards, devastating coastal towns and villages and claiming tens of thousands of lives. The eruption also injected an immense volume of ash and sulfur dioxide into the high atmosphere, where it circled the globe for years. This atmospheric veil scattered sunlight, creating spectacular, vibrant sunsets worldwide, which were captured in the paintings of artists like Edvard Munch, and it also caused a noticeable drop in global temperatures, a profound and tragic demonstration of how a single geological event can touch the entire planet. The eruption of Mount Vesuvius in 79 AD stands as one of history's most poignant encounters between human civilization and volcanic power. When the volcano awoke, it did not immediately destroy the Roman cities of Pompeii and Herculaneum, but instead buried them in a way that preserved their final moments for millennia. Pompeii was covered in a thick blanket of ash and pumice, while Herculaneum was entombed by devastating pyroclastic flows that carbonized wood and organic materials. The event was chronicled by Pliny the Younger, who described the towering pine tree-shaped cloud, giving us the scientific term Plinian eruption. For nearly 2,000 years, these cities lay sleeping beneath the earth, forgotten. When rediscovered and excavated, they provided a perfect, frozen-in-time snapshot of Roman life, from the bread left in ovens to the vibrant frescoes on the walls. A solemn and detailed time capsule sealed by the very mountain that had lived in its shadow. The super eruption of Lake Toba in Indonesia, which occurred about 74,000 years ago, was the largest known volcanic event in the last 25 million years. This was an eruption on a scale that dwarfs human comprehension, ejecting an estimated 2,800 cubic kilometers, or nearly 700 cubic miles, of material, enough to cover the entire state of Texas in a layer of ash several feet deep. The aftermath of this event was a volcanic winter that likely lasted for years, as the immense cloud of sulfur aerosols reflected sunlight and caused a significant, perhaps drastic, cooling of the global climate. Some scientists have proposed a volcanic bottleneck in human evolution linked to this event, suggesting that the resulting climate change may have reduced human populations and forced our ancestors to adapt, while other researchers argue that the evidence for such a drastic global bottleneck is still uncertain. Today, the serene Lake Toba fills the enormous caldera left behind, its peaceful waters a beautiful, placid mask, covering the memory of an event that nearly rewrote the story of life on Earth. The longest continuous volcanic chain on Earth is not on land, but is hidden deep beneath the ocean waves, forming the mid-ocean ridge system. This global system of underwater mountains winds its way around the planet for over 40,000 miles, or about 65,000 kilometers, like the seam on a baseball. This is where the planet is actively pulling itself apart, a process known as seafloor spreading. As the tectonic plates diverge, magma from the mantle rises to fill the gap, erupting quietly and continuously onto the ocean floor. This magma cools to form new oceanic crust, the vast fields of pillow lava we spoke of earlier. This entire mountain range is, in essence, a single planet-spanning fissure volcano, constantly at work, building the very floor of the world's oceans. It is a silent, immense, and patient engine of creation, where the Earth's crust is forever renewed, far from the sun and human eyes, in the cold, dark pressure of the deep. The Hawaiian Islands are a classic example of hotspot volcanism, a process that builds volcanoes far from the edges of tectonic plates. Deep within the Earth's mantle, in a fixed location, a plume of exceptionally hot material, a mantle plume or hotspot, rises and partially melts as it nears the surface, creating a vast, persistent source of magma. Above this stationary hotspot, the Pacific plate moves slowly but inexorably, like a conveyor belt traveling over a candle flame. As the plate drifts to the northwest, the hotspot punches through the crust, creating a volcano over millions of years. As the plate moves, this volcano is carried away from the magma source and becomes dormant, and a new volcano begins to form in its place. This process has created the entire Hawaiian Emperor Seamount chain, a long, visible trail of islands and submerged mountains stretching thousands of miles, a geological breadcrumb trail that perfectly records the motion of the Pacific plate over its unmoving fiery origin. Geysers and hot springs are not volcanoes themselves, but they are close relatives, the beautiful and gentle children of volcanic heat. These are known as hydrothermal features, and they exist where groundwater seeps deep into the earth and comes into contact with, or proximity to, a body of magma that is cooling far below. In a hot spring, this heated water, now buoyant, simply rises back to the surface, dissolving minerals along the way and creating colorful, steaming pools. A geyser, like Old Faithful in Yellowstone, is more complex, requiring a specific underground plumbing system of chambers and constrictions. The water is superheated by the volcanic rock, but the pressure of the water column above it prevents it from boiling until it finally flashes into steam, expands dramatically, and erupts in a glorious temporary fountain. These features are a sign of the hidden fire, a way for the Earth's deep warmth to express itself not in rock, but in steam and water. The most volcanically active body in our entire solar system is Io, a moon of the planet Jupiter. Io is a world of constant, violent, and spectacular eruptions, a stark contrast to the icy moons that are its neighbors. Its incredible geologic engine is not driven by internal radioactive decay, as Earth's is, but by the relentless pull of Jupiter itself. Io is caught in a gravitational tug-of-war between the immense gravity of Jupiter and the smaller, periodic tugs from its sibling moons, Europa and Ganymede. This constant squeezing and stretching, known as tidal flexing, generates enormous friction deep within Io's core and mantle, heating its interior to the point where it becomes a molten, fiery hellscape. This heat escapes to the surface through over 400 active volcanoes, which spew plumes of sulfur and sulfur dioxide hundreds of miles or kilometers high, painting the moon in garish shades of yellow, red, and black. A truly dynamic and tormented world. A volcanic winter is a potential global climate effect that can follow a truly massive, explosive volcanic eruption. This is not caused by the ash, which, while disruptive, falls out of the atmosphere relatively quickly. The true culprit is sulfur dioxide. When a volcano injects millions of tons of this gas high into the stratosphere above the weather, it reacts with water vapor to form a haze of tiny sulfuric acid droplets, or aerosols. This fine, reflective mist can persist for several years, encircling the globe and scattering incoming sunlight back into space before it can warm the planet's surface. The result is a noticeable, widespread cooling, a decrease in global average temperatures that can disrupt weather patterns, shorten growing seasons, and lead to food shortages. This is the planet's own dimming switch, a powerful reminder that the atmosphere is a delicate shared space, vulnerable to the chemical breath of the deep earth. The 1815 eruption of Mount Tambora in Indonesia was the largest volcanic eruption in recorded human history, a colossal event far exceeding Krakatoa or Mount St. Helens. The eruption itself was a cataclysm, ejecting a staggering volume of rock and ash and creating pyroclastic flows that devastated the surrounding islands. But its most far-reaching effects were atmospheric. Tambora injected such an enormous quantity of sulfur dioxide into the stratosphere that it triggered a severe volcanic winter, leading to the infamous year without a summer. In 1816, across Europe and North America, temperatures plummeted, leading to crop failures, famine, and widespread hardship. Snow fell in New England in June, and the cold, damp weather in Europe is famously credited with inspiring Mary Shelley to write Frankenstein. During a gloomy holiday, Tambora was a stark illustration of global interconnectedness, a single mountain on a remote island that reached out to change the weather for the entire world. Hawaiian folklore beautifully personifies the volcanic glass created by Kilauea's eruptions, naming these delicate formations after the volcano goddess, Pele. When fluid, basaltic lava is ejected into the air during a fiery fountain, it can be stretched and shaped by the wind in fascinating ways. Pele's tears are small, black, teardrop-shaped or spherical beads of volcanic glass, formed as tiny droplets of lava cool and solidify almost instantly in mid-air. Pele's hair forms when these same droplets are stretched by the wind into incredibly fine, long, and flexible strands of glass, often just a few micrometers thick, which can drift for many miles. These golden green, hair-like filaments can accumulate in mats on the ground, beautiful but also sharp and abrasive. These poetic formations are a tangible, delicate record of a fiery, windswept moment, a snapshot of liquid rock caught and frozen by the air before it could ever touch the ground. The Deccan Traps in modern-day India are the remnants of one of the largest volcanic features on Earth, a testament to a period of unimaginable eruptive activity. This is not a single volcano, but a vast, large igneous province, an enormous expanse of land built from successive, voluminous floods of basaltic lava. Around 66 million years ago, eruptions lasting for tens of thousands of years poured out layer upon layer of molten rock, ultimately covering an area of over 500,000 square kilometers, or 190,000 square miles, and accumulating in some places to a thickness of over 6,500 feet, or 2,000 meters. The timing of this immense volcanic event coincides closely with the extinction of the dinosaurs, and it is a subject of intense scientific debate. While the Chicxulub asteroid impact is the primary cause, it is widely believed that the massive climate-altering gas release from the Deccan Traps played a significant role, helping to create a 1-2 punch that dramatically stressed the global ecosystem and sealed the fate of the planet's previous rulers. While the Deccan Traps were vast, The Siberian traps represent the largest known flood basalt eruption in Earth's history, an event of truly world-ending proportions occurring around 252 million years ago. This volcanic cataclysm marks the boundary between the Permian and Triassic periods. Over a span of perhaps 1 million years, a staggering volume of magma, estimated in the millions of cubic kilometers, erupted across a vast area of what is now Siberia, burying it in lava. The environmental consequences were catastrophic. The massive release of carbon dioxide and other greenhouse gases led to runaway global warming, while other gases acidified the oceans. This event is directly and strongly linked to the Great Dying, the Permian-Triassic extinction, the most severe extinction event in our planet's history, which wiped out over 90% of all marine species and 70% of terrestrial life. The Siberian traps are a silent, rocky monument to the time the Earth's own inner fire almost extinguished life on its surface. The destructive power of volcanoes is often balanced by a profound, life-giving legacy, incredibly fertile soil. Volcanic ash, pumice, and lava are not like typical soil. They are freshly minted rock, rich in essential minerals like potassium, phosphorus, and trace elements that plants need to thrive. When this new material is first deposited, it is sterile and lifeless. But over time, through the patient work of weather, rain, wind, and chemical breakdown, this volcanic debris, especially the porous ash, weathers and crumbles. It transforms into soils that are exceptionally good at holding water and nutrients, creating some of the most productive and lush agricultural lands on the planet. This is why, despite the inherent risks, civilizations have always been drawn to the slopes of volcanoes, from the vineyards on Mount Etna to the coffee plantations in Colombia, a timeless cycle of destruction and renewal, where the mountain's fire ultimately provides the bounty for the land. Obsidian is a stunning natural glass, a prized material formed by the unique cooling process of a specific type of lava. It is born from magma that is extremely rich in silica, making it highly viscous or thick. When this pasty lava erupts, it cools so rapidly upon contact with the air or water that the molecules within it have no time to arrange themselves into an orderly, crystalline structure, as they would in a rock like granite. Instead, they are frozen in place, a disordered, solid snapshot of the liquid state, creating a glass. This material has a unique property called conchoidal fracture, meaning it breaks with curved, smooth, and incredibly sharp edges. For millennia, ancient cultures, from the Aztecs to the Native Americans, recognized its value, skillfully napping obsidian to create razor-sharp tools, arrowheads, and blades, far sharper than steel, a material born of fire and speed, valued for its perfect cutting edge. Pumice is the curious rock that floats, a geological marvel that defies our expectation of stone's weight and density. It is created during explosive eruptions from magmas that are very high in silica and, crucially, extremely rich in dissolved gases, mostly water and carbon dioxide. As this magma surges to the surface, the sudden drop in pressure causes the dissolved gases to expand and exsolve, or come out of solution, exactly like the carbon dioxide in a soda bottle when you open the cap. This creates a seething, fiery froth of molten rock and gas bubbles. If this froth cools and solidifies very quickly, the bubbles are trapped, creating a rock that is essentially a glassy, solid foam. The resulting pumice is so lightweight, its volume so full of empty gas pockets, that its overall density is less than that of water, allowing it to float. a stone that remembers the air and gas that gave it its lightness. Fumaroles are vents or openings in the Earth's crust, often found on the flanks or in the craters of active volcanoes, from which hot volcanic gases and steam escape into the atmosphere. They are a sign that a volcano is alive and breathing, even if it is not actively erupting lava. These gases, which include water vapor, sulfur dioxide, carbon dioxide, and hydrogen sulfide, are released from the magma chamber that still simmers deep below. As these hot, often acidic gases rise, they can interact with the surrounding rock and groundwater, and the sulfurous gases often deposit brilliant yellow crystals of pure sulfur around the vent opening, creating a striking, otherworldly landscape. Fumaroles are a volcano's exhaust pipe, a way for the sleeping giant to release pressure and exhale its chemical breath, offering scientists a direct, if pungent, window into the chemistry of the magma hidden far beneath their feet. Volcanology is the name of the science that seeks to understand these magnificent and powerful features of our planet. It is a discipline that combines the rigorous work of geology, chemistry, and physics with the tangible, often dangerous, work of field observation. Volcanologists are the Earth's biographers, the listeners who place their instruments on the flanks of sleeping giants to monitor their heartbeat. They measure the subtle swelling of the ground as magma rises. They sample the chemical breath of fumaroles, and they map the ancient, cooled rivers of lava to reconstruct a mountain's life story. Their work is to decipher the complex language of the planet's interior, to understand the why and how of eruptions, not just to marvel at the power, but to provide the forecasts and understanding that allow people to live more safely in the shadow of these awesome, creative, and ever-changing mountains. One of the most important warning signs that a volcano may be preparing to erupt is an increase in seismic activity, a trembling of the ground. Magma is not a static, still pool. As it begins to move from a deep chamber towards the surface, it must force its way through solid rock. This upward movement cracks the rock, creating a series of small, shallow earthquakes. These earthquakes are often too small to be felt by people, but they are easily detected by sensitive seismometers placed around the volcano. A particularly telling signal is harmonic tremor, a continuous, low-frequency vibration that is not a sharp jolt, but a steady, rhythmic humming. This tremor is believed to be the signature sound of magma itself, resonating as it flows through the Earth's underground plumbing, a deep, telltale song that signals the mountain is truly beginning to stir from its slumber. Another crucial sign of an awakening volcano is the deformation or swelling of the ground surface. Before an eruption, magma from deep within the Earth often accumulates in a shallower magma chamber, a reservoir miles beneath the volcano's summit. As this chamber fills, it is like inflating a balloon underground. The immense volume of new material pushes the overlying rock upwards and outwards. This swelling, or inflation, is almost imperceptible to the naked eye, but it can be measured with incredible precision by modern instruments. Tilt meters, which are like hypersensitive carpenter's levels, can detect changes in the slope of the mountain down to a fraction of a degree. More recently, satellite-based GPS and radar, INSAR, can map this ground movement from space, revealing a slow, steady breathing of the mountain as the pressure from below builds. A silent, physical warning that the volcano is taking a deep breath before it speaks. The chemical composition of volcanic gases can provide vital clues about the state of the magma below. As magma rises and the pressure upon it decreases, dissolved gases begin to escape, finding their way to the surface through fumaroles and the volcano's main vent. Volcanologists collect these gases, often in dangerous and difficult conditions, to analyze their contents, measuring the ratios of gases like carbon dioxide to sulfur dioxide, or the presence of hydrogen chloride. A significant increase in the amount of sulfur dioxide, for instance, is a classic indicator that a fresh, gas-rich batch of magma is rising to a shallow depth. As sulfur is much more readily released at lower pressures, these silent chemical whispers from the deep are one of the most reliable methods for forecasting an eruption, a change in the mountain's breath that often precedes a change in its behavior, offering a premonition of the fire to come. The largest eruption of the 20th century did not come from a well-known volcano, but from a remote, ash-filled valley in Alaska in 1912. This event, now known as the eruption of Novaropta, was a colossal Plinian eruption that expelled over 3.1 cubic miles, or 13 cubic kilometers, of magma, far more than Mount St. Helens. The eruption was so massive that it caused the summit of a nearby, unrelated volcano, Mount Katmai, to collapse. As the magma chamber that fed Novaropta was partially drained, for days the sky was darkened by ash, which fell as far away as Washington state. The most spectacular legacy of the event was the creation of the Valley of 10,000 Smokes, a vast, once steaming plain where the superheated ash flow, a massive pyroclastic deposit, cooled and released gases through countless fumaroles for years, a stark, grey and moon-like landscape, born in a single fiery instant. The word volcano itself has its roots in the mythology of the ancient Romans. It derives from the name Vulcan, the Roman god of fire, metalworking, and the forge, who was the counterpart to the Greek god Hephaestus. The Romans believed that the volcanic island of Volcano, located in the Tyrrhenian Sea just north of Sicily, was the chimney of Vulcan's subterranean forge, where he crafted the weapons for the gods, including the thunderbolts for Jupiter. When the mountain rumbled, sparked, and smoked, it was simply a sign that Vulcan was at work, hammering a new blade or stoking his eternal fire. This ancient personification of the Earth's heat and power has endured, and so we have given the name of this ancient, divine craftsman to every fire mountain on Earth, a timeless link between the mythic imagination and the geologic reality. The island of Surtsey, off the southern coast of Iceland, is one of the youngest pieces of land on Earth, a place where scientists were able to watch geology in fast forward. The island did not exist before November 1963, when an undersea eruption, part of the Mid-Atlantic Ridge System, breached the ocean's surface. A local fishing boat, investigating what they thought was a fire on the water, was the first to witness the birth of this new land, as a column of black ash and steam rose from the waves. The eruption continued for 3.5 years, a constant battle between the lava and the sea, ultimately building an island that covers about 1 square mile, or 2.7 square kilometers. Surtsey was immediately declared a protected natural laboratory, a pristine environment where scientists could study how life, from the first bacteria and mosses to the eventual arrival of birds and seals, begins to colonize a completely sterile, brand new volcanic world. Mount Erebus, located on Ross Island in Antarctica, holds the distinction of being the southernmost active volcano on Earth. This icebound giant rises to an elevation of over 12,400 feet, or 3,790 meters, and it stands in one of the most inhospitable environments on the planet, a world of permanent ice and profound cold. Yet, despite the frozen landscape, Mount Erebus is constantly, quietly active. It is one of the very few volcanoes in the world to host a persistent, convecting lava lake in its summit crater, a visible pool of molten rock that bubbles and seethes, its fiery glow a stark contrast to the surrounding ice. The volcano's activity also creates a unique network of ice caves, hollowed out by the hot volcanic gases that escape from fumaroles, melting the overlying snow and ice to form intricate, crystal-lined tunnels, a hidden, warm labyrinth beneath the frozen surface. The East African Rift Valley is a place where a continent is slowly, but inexorably, tearing itself apart, and this process is fueling a unique line of volcanoes. This vast geological feature, a divergent plate boundary, stretches for thousands of miles from the Red Sea down through Ethiopia, Kenya, and Tanzania here. The African continent is splitting into two new plates, the Nubian and Somali plates, at a rate of a few millimeters per year. As the continental crust stretches thin, like taffy being pulled, the hot mantle beneath it rises to fill the space, melting to create magma. This process feeds a chain of volcanoes, including the famous Mount Kilimanjaro, the highest peak in Africa, and Old Doinyo Lengai, a truly unique volcano. This rift is a portrait of geology in motion, a nascent ocean in the making, and a glimpse into how continents are born and how they die, all written in a language of earthquakes and fire. The volcano Old Doinyo Lengai in Tanzania is the only active volcano on Earth that erupts a type of lava known as nitrocarbonatite. This lava is utterly unique. It is not the familiar silica-based molten rock of other volcanoes, but a molten carbonate rich in sodium and potassium. It erupts at incredibly low temperatures for lava, at only around 500 to 600 degrees Celsius, or 930 to 1100 degrees Fahrenheit, which is so cool that it does not glow bright red or orange during the day, but appears as a fluid black oil. At night, however, it glows a dull cherry red. Because this lava is water-soluble, it weathers and breaks down extremely quickly upon contact with rain. When it first erupts and cools, it is a dark black, but within hours, it chemically alters in the moist air, turning into a white, powdery substance, blanketing the mountain in what looks like snow. It is a geological marvel, a cold volcano that paints the African landscape in shades of black and white. The city of Auckland in New Zealand is in the unique and somewhat precarious position of being built directly on top of an active volcanic field. This is not a single large volcano, but a monogenetic field, meaning it is dotted with around 53 small individual volcanoes, each of which erupted only once. These features, including iconic cones like Mount Eden and One Tree Hill, as well as the water-filled caldera of Lake Pupuke, were all born from separate, short-lived eruptions over the last 250,000 years. The most recent, Rangitoto Island, formed in the harbour only about 600 years ago, a dramatic event witnessed by the Maori people who inhabited the area. While the existing cones will never erupt again, the magma source beneath the city is still active, meaning that the next eruption, when it eventually comes, will not reawaken an old volcano, but will burst forth to create a brand new one in an unpredictable location somewhere within the city's sprawling suburbs. A kimberlite pipe is a rare and specific type of volcanic conduit that is the primary source of the world's diamonds. These structures are not the product of the volcanoes we typically imagine, but are deep, carrot-shaped pipes of rock that were emplaced with incredible speed and violence from deep within the mantle, at depths of over 90 miles or 150 kilometers. This is the diamond stability zone, where the immense pressure and heat are just right for carbon to crystallize into diamond. The magma that formed these pipes, known as kimberlite magma, was likely very fluid and extremely rich in gases like carbon dioxide. It is thought to have blasted to the surface at supersonic speeds, a geological cannon shot that carried these precious, high-pressure minerals, the diamonds, up to the surface as passengers, entombing them in the solidified, dark, igneous rock, a rapid, violent gift from the deepest parts of the earth. Mount Etna, on the eastern coast of Sicily, is Europe's largest and most active volcano, a mountain whose story is woven deeply into the fabric of Mediterranean history and myth. Unlike Mount Vesuvius, which has long periods of quiet dormancy, Etna is in a state of near-constant activity, a persistently active volcano. Its eruptions range from quiet, effusive lava flows that ooze from flank vents, slowly building its slopes, to more dramatic, short-lived explosive bursts from its summit craters, known as paroxysms, which create spectacular fountains of fire. This reliable activity has made it a subject of fascination and a natural laboratory for millennia. From the forges of Hephaestus in Greek myth to the modern volcanologists who monitor it daily, Etna is not just a geological feature, it is a cultural one, a mountain that both threatens and provides. Its fertile, mineral-rich slopes supporting vineyards and orchards, a true living giant that has coexisted with civilization for thousands of years. The United States Geological Survey, or UGS, operates a network of volcano observatories designed to monitor the nation's most hazardous volcanoes. The first of these, the Hawaiian Volcano Observatory, or HVO, was founded in 1912 on the rim of Kilauea's caldera, a pioneering effort to apply systematic scientific observation to an active volcano. Today, this network has expanded to include observatories in Alaska, the Cascade Range, Yellowstone, and California. These centers are the nerve centers of volcanic monitoring, staffed by scientists who watch the planet's pulse around the clock. They use an array of instruments, seismometers, GPS receivers, gas sensors, and satellites, to detect the subtle changes in seismic activity, ground deformation, and gas emissions that are the telltale signs of waking magma. Their mission is to understand these complex systems, not just for the sake of knowledge, but to provide the timely warnings and hazard assessments that are crucial for protecting communities living in the shadow of these sleeping giants. Pele's, the legendary Hawaiian goddess of volcanoes, fire, and creation, is a powerful figure who personifies the dual nature of Kilauea, and Mauna Loa. She is not a distant, abstract deity, but a living, tangible presence, and her stories are the geological and cultural history of the islands. In Hawaiian oral tradition, she is the Kini Aqua, the creator of the islands, whose fiery temperament and passionate nature are expressed in the eruptions themselves. When lava flows, it is said to be the goddess traveling across the land, reshaping her domain. This belief fosters a deep and profound respect for the volcano, not just as a natural hazard, but as a sacred, creative force. This cultural framework provides a way to understand and coexist with one of the most active volcanic systems on Earth, a relationship built not on fear, but on reverence for the awesome, life-giving power of the land itself. A limnic eruption is a rare and silent disaster, a deadly phenomenon that occurs not from a volcano of rock, but from a volcanically fed lake. This occurs in deep lakes that are located above areas of volcanic activity, where carbon dioxide gas seeps from the Earth's magma and dissolves into the cold, deep bottom waters. Accumulating in high concentrations over many years, the lake becomes a stratified, stable trap, with the deep water becoming supersaturated with this invisible gas. This stability can be suddenly overturned by a trigger, such as a landslide, an earthquake, or even just heavy rain. This disturbance causes the deep, gas-rich water to rise, and as the pressure on it decreases, the dissolved carbon dioxide comes violently out of solution, just like opening a shaken can of soda. The 1991 eruption of Mount Pinatubo in the Philippines was a landmark event, not just for its sheer power, but for being one of the most successfully forecasted major eruptions in modern history. After 500 years of dormancy, the volcano began to stir, with escalating earthquakes, steam explosions, and the growth of a lava dome. A joint team of Filipino and American volcanologists, primarily from the USGS, raced to install a network of monitoring equipment. Based on the seismic data and the explosive increase in sulfur dioxide emissions, they recognized the signs of a massive gas-rich magma body ascending. They lobbied tirelessly for evacuations, creating hazard maps that ultimately convinced the government and the US military to evacuate tens of thousands of people from the surrounding areas, including the massive Clark Air Base when the volcano finally unleashed its cataclysmic Plinian eruption, one of the largest of the 20th century. Thousands of lives were saved, a true and powerful testament to the life-saving value of volcanology and the courage to heed its warnings. The Volcanic Explosivity Index, or VEI, is the yardstick by which scientists measure the power and magnitude of an explosive volcanic eruption. Developed in the 1980s, this scale is similar in concept to the Richter scale for earthquakes, but it measures a different set of criteria. The VEI is a logarithmic scale, running from 0 to 8, where each successive number represents an eruption at least 10 times more powerful than the last. The scale is based primarily on the volume of volcanic material, or tephra, that is ejected, as well as the height that the eruption column of ash and gas reaches in the atmosphere, and the duration of the eruption. A small, gentle Hawaiian-style eruption is a VEI0 or VEI1. The 1980 eruption of Mount St. Helens was a VEI5. The 1815 Tambora eruption was a VEI7, and a super eruption like Yellowstone or Toba would be a VEI8, a planet-altering event of almost unimaginable scale. The 1783 eruption of the Laki fissure in Iceland, known as the Skaftareldar or Fires of Skaftar, was a basaltic flood eruption that had devastating consequences for the entire northern hemisphere. This was not a single explosive event from a mountain peak, but a 9-month-long effusive eruption from a 17-mile or 27-kilometer long fissure that poured out an enormous volume of fluid lava covering over 230 square miles or 600 square kilometers of land. While the lava itself was a local disaster, the real catastrophe was the gas. The fissure released a colossal plume of sulfur dioxide and hydrogen fluoride, creating a poisonous Laki haze that settled over Iceland, killing over half of the island's livestock and leading to a famine that wiped out a quarter of the human population. This toxic haze drifted across Europe, causing a spike in mortality and crop failures. A grim reminder that even a quiet, effusive eruption, if large enough, can have a profound and deadly impact on the global atmosphere. The search for life beyond Earth is increasingly focused on worlds with volcanic activity, particularly those with water. On Earth, we have discovered entire ecosystems in the deep ocean, thriving in total darkness, clustered around hydrothermal vents, which are essentially underwater volcanic hot springs. These black smokers spew superheated, mineral-rich water from the planet's interior. Instead of using sunlight for energy, the life here, strange tube worms, crabs, and vast mats of bacteria, relies on chemosynthesis, a process of deriving energy from the chemical reactions of the sulfur compounds gushing from the vents. This discovery has revolutionized our understanding of life, suggesting it doesn't need the sun, just water, heat, and a chemical gradient. This makes icy moons like Saturn's Enceladus, which has been observed erupting plumes of water and organics from a subsurface ocean heated by tidal flexing, one of the most tantalizing places to search for life, a hidden volcanic watery cradle in the dark. The island of Heimaey in Iceland experienced a dramatic volcanic event in 1973 that showcased an incredible human effort to coexist with an eruption. In the middle of a January night, a new volcanic fissure suddenly tore open on the edge of Vestmannaeyjar, the island's main town and Iceland's most important fishing port. Lava flows and ashfall began to consume the town, and most critically, threatened to flow into and completely block the narrow entrance to the harbour, which would have destroyed the town's economy and livelihood. In a remarkable and audacious feat of engineering and determination, the islanders, with international help, decided to fight the lava. For months, they ran a massive system of pipes and pumps, spraying millions of gallons of cold seawater directly onto the advancing edge of the lava flow. This effort successfully cooled and solidified the lava front, diverting it just enough to save the vital harbour, a rare and hard-won battle where humanity managed to steer the path of a river of stone. During highly explosive volcanic eruptions, a spectacular and dangerous phenomenon known as volcanic lightning can occur. This is not lightning descending from a thundercloud, but lightning generated from within the eruption plume itself. As the volcano blasts a turbulent column of ash, rock, and gas high into the atmosphere, the tiny, jagged particles of ash and ice crystals collide with incredible friction. This collision strips electrons from the particles, creating an immense separation of static charge within the cloud. Just as in a regular thunderstorm, the top of the plume often becomes positively charged, while the bottom becomes negatively charged. When this electrical potential grows strong enough to overcome the resistance of the air, it discharges in a brilliant, terrifying flash of lightning, a jagged fork of light illuminating the swirling dark clouds of ash, a moment where the planet's fire and its atmospheric electricity meet in a single, awesome display. The Giant's Causeway in Northern Ireland is a breathtaking natural wonder, composed of tens of thousands of interlocking, mostly hexagonal basalt columns, a masterpiece of geological geometry. This striking formation is not the work of mythic giants, but the slow, patient result of a cooling lava flow some 60 million years ago. A thick, molten flow of basaltic lava, spreading across the landscape, began to cool and contract. As it cooled from the top surface downwards, it cracked, much like mud cracks in a drying lake bed, but in a far more uniform way. Because this was a thick, homogeneous layer, the contraction stresses were distributed evenly, and the most efficient way to relieve this stress is to form hexagonal cracks. These cracks then propagated deep down into the flow as the cooling front advanced, creating the array of tall, elegant, and strangely perfect pillars we see today, a silent, frozen testament to the physics of cooling rock. There is a curious geological feature known as a mud volcano, which, despite its name, has almost nothing in common with the magmatic volcanoes of fire and rock. Mud volcanoes are not typically hot, and they do not erupt molten lava. Instead, they are formed in regions where pressurized gases, primarily methane, along with water and fine sediment, are forced to the surface from deep underground. These conditions are often found in areas with tectonic activity, where layers of sediment are rapidly buried and compacted, trapping gases. This pressure finds a weak point, and the gas-rich slurry percolates upwards, forming a conical mound or a bubbling pool of mud on the surface. These can range from small, hand-sized griffins to large hills, all quietly or sometimes messily burping gas and mud, a much colder, gassier, and gentler expression of the Earth's internal pressures, a cold breath rather than a fiery one. The 2010 eruption of Eyjafjallajökull in Iceland, while relatively small in volcanic terms, brought global air travel to a standstill, revealing a critical vulnerability of the modern world. The problem was not the volume of the eruption, but its nature. It was an explosive eruption that occurred beneath a glacier. The interaction of the hot magma with the melting ice water created a plume of incredibly fine, sharp, and abundant volcanic glass ash. This ash cloud was carried by the prevailing winds directly over the high-traffic air corridors of Europe. When this microscopic abrasive glass dust is drawn into a jet engine, it does not just pass through. The engine's operating temperature, which is over 1,000 degrees Celsius or 1,800 degrees Fahrenheit, is hot enough to melt the ash, turning it back into a sticky molten glass that coats the turbine blades and fuel nozzles, causing the engines to stall and fail. This event was a profound reminder that our most advanced technologies are still vulnerable to the most ancient elemental forces of the planet. A Strombolian eruption is a style of volcanic activity named after the volcano Stromboli, a small island off the coast of Italy that has been erupting almost continuously for at least 2,000 years. This has earned it the nickname Lighthouse of the Mediterranean. A Strombolian eruption is not a steady flow of lava, nor a cataclysmic explosion, but rather a series of distinct, rhythmic, and relatively mild bursts deep within the volcano's conduit. Large bubbles of gas accumulate and rise through the magma. When these bubbles reach the surface of the magma column, they burst with a mild, throaty pop, throwing incandescent blobs of lava or spatter into the air in a fiery, fountain-like spray that lasts for a few seconds. These periodic, almost gentle exhalations are like the Earth's own deep, fiery heartbeat, a steady, predictable rhythm of fire that has guided sailors and fascinated observers for millennia. A volcanian eruption is a significantly more violent and dramatic event, named for the island of Volcano, the mythological forge of the Roman god. This type of eruption is characterized by a short, powerful, cannon-like explosion that clears the volcano's throat. It typically occurs after a period of dormancy, during which a plug of viscous, solidified lava or debris has formed in the volcano's vent, sealing the magma chamber below. As gases and pressure build up beneath this cap, it is like a cork in a champagne bottle. Until the pressure becomes too great to contain, the volcano then erupts with a single, loud detonation, shattering the plug and sending a dense, towering column of ash, rock, and volcanic bombs high into the atmosphere, often several miles or kilometers up. This is followed by a period of quiet as the pressure is released before the cycle begins anew, a powerful, percussive reminder of the immense pressures that can build within a sleeping mountain. Plinian eruptions are among the most powerful and feared of all volcanic events, named for Pliny the Younger, who gave the first written description of one during the eruption of Vesuvius in 79 AD. This is not a short burst, but a sustained, cataclysmic eruption that can last for hours or even days. The defining feature is a towering, jet-like column of hot gas, ash, and pumice that is blasted high into the stratosphere, often reaching 15 to 30 miles or 25 to 50 kilometers above the Earth. As this massive column is held aloft by the sheer, continuous force of the eruption, it can eventually lose its upward thrust, or its edges can cool and become too heavy, causing parts of it to collapse back to Earth. This collapse generates the most devastating of all volcanic hazards, the searing, fast-moving pyroclastic flows that sweep down the volcano's flanks, a truly awesome and overwhelming display of the planet's explosive potential. A Plinian eruption is a particularly deadly type of event, named after the 1902 eruption of Mount Pelée on the island of Martinique, which tragically destroyed the city of Saint-Pierre. The hallmark of a Plinian eruption is not a vast vertical Plinian column, but the generation of a fast-moving, ground-hugging pyroclastic flow. This often occurs when a volcano erupts very thick, viscous, silica-rich lava that is too sticky to flow, so it piles up in the crater to form a lava dome. As this dome grows, it becomes unstable, and it can either collapse under its own weight or be blown apart by trapped gases. This unleashes a dense, superheated avalanche of ash, gas, and rock, a nuée ardente, or glowing cloud, that is heavier than air and races down the volcano's flanks at hurricane speeds, a silent, grey, and utterly devastating flow that follows the contours of the land. When we think of volcanic glass, we usually picture obsidian, the translucent, silica-rich glass used for ancient tools. However, there is another, more common but less famous type of volcanic glass, known as tachylite. While obsidian forms from the rapid cooling of high silica, viscous rhyolitic lava, tachylite forms from the rapid cooling of low silica, fluid basaltic lava, the same lava that builds Hawaii. When this fluid lava cools very quickly, such as when it flows into water or is ejected as a fine spray, its minerals have no time to crystallize, and it freezes into a glass. Unlike obsidian, tachylite is not a pure, clear glass. It is opaque, black, and often has a dull or waxy luster. It is more a snapshot of the molten basalt, a common rock caught in a rare moment of speed, a reminder that even the most fluid lavas can become glass if they are robbed of their time to cool slowly. The immense heat slumbering beneath the Earth's crust, the same heat that fuels volcanoes, is a powerful and remarkably clean source of renewable energy known as geothermal energy. In volcanically active regions, magma chambers or bodies of intensely hot rock lie relatively close to the surface, creating a vast natural reservoir of heat. Geothermal power plants tap into this ancient subterranean warmth. In some systems, they draw up naturally occurring hot water or steam from deep underground to spin a turbine and generate electricity. In other, more modern, enhanced systems, cold water is pumped down through one well, forced to fracture through the hot rock to heat up, and then drawn back to the surface as superheated steam through a second well. This is the Earth's own internal fire, harnessed not as a destructive force, but as a constant, reliable, and sustainable source of power, a way to light our homes using the planet's own living, breathing warmth. Our solar system's shield volcanoes are not limited to Earth or even the mighty Olympus Mons on Mars. The Red Planet is home to several other colossal mountains, including a trio of giants known as the Tharsis Montes. These three volcanoes, Arsia Mons, Pavonis Mons, and Ascraeus Mons, are arranged in a vast diagonal line on the Tharsis Bulge, a huge volcanic plateau. Like Olympus Mons, these are shield volcanoes of almost unimaginable scale, each one far larger than the entire Hawaiian island chain, their summits reaching heights of 10 to 12 miles, or 16 to 19 kilometers, above the Martian plains. Their sheer size, once again, is a testament to the unique geology of Mars: a thick, static crust, lower gravity, and a long-lived mantle plume. They now stand as silent, cold monuments, their fires extinguished for eons, a vast, quiet family of giants sleeping beneath the thin, dusty red sky, a frozen memory of Mars's fiery and dynamic past. The global cooling that follows a major eruption, the volcanic winter, is a direct consequence of a process called the volcano albedo effect. Albedo is a measure of how reflective a surface is. Pure white snow has a high albedo, reflecting sunlight, while dark, black asphalt has a low albedo, absorbing it. When a massive eruption, like Pinatubo in 1991, injects millions of tons of sulfur dioxide into the stratosphere, this gas converts into a fine mist of sulfuric acid aerosols. This high-altitude haze acts like a vast, subtle mirror, increasing the albedo of the entire planet. The fine droplets are incredibly effective at scattering and reflecting incoming solar radiation back into space before it can reach and warm the lower atmosphere and the surface. This is the Earth's own protective, if accidental, sunshade, a chemical veil that temporarily dims the world and reminds us of the profound, delicate connection between the deep geology below and the fragile climate above. Kilauea volcano in Hawaii is one of the most active on Earth, and its heart is the Halemaumau crater, a feature steeped in both geology and legend for much of the last century, and for long periods in its history. Halemaumau hosted a persistent, bubbling lake of molten lava, a dynamic, churning pool of liquid rock. This lava lake, often rising and falling, was considered by Hawaiians to be the home of the goddess Pele. In 2018, a major eruption on the volcano's flank caused this lava lake to completely drain away, like water from a bathtub, leading to the collapse of the crater floor. But the mountain is always remaking itself, and in 2020, water began to seep into the new, deep pit, forming a lake for the first time in recorded history, only to be boiled away and replaced, once again, by a new, rising lava lake. Halemaumau is a true geologic theatre, a constantly changing stage that reveals the restless, cyclical, and creative spirit of the volcano. Volcanic bombs are fascinating. Sculptural projectiles form during explosive eruptions. These are not just angular, shattered rocks, but are instead pieces of magma or molten lava that are ejected from the vent in a liquid or semi-liquid state. As these fiery blobs fly through the air, they are twisted, stretched, and shaped by the forces of aerodynamics, and they cool and solidify before they hit the ground. This process creates a variety of characteristic shapes, Spindle bombs are twisted and pointed at both ends from spinning through the air. Ribbon bombs are long and flattened. Bread crust bombs develop a cracked outer crust as the outside cools and hardens, while the inside remains hot and gassy, causing the surface to expand and break. These formations are essentially frozen moments of a fiery flight, natural sculptures molded by fire and air, landing on the ground as solid, aerodynamic reminders of the eruption's power. Lapilli is a term used by volcanologists to classify a specific size of tephra, which is the all-encompassing word for any material, regardless of size or composition, that is ejected from a volcano during an eruption. The word lapilli is Italian for little stones, and that is precisely what they are. Geologically, they are defined as fragments of ejected material that range in size from 2 millimeters to 64 millimeters, which is roughly the size of a pea up to the size of a walnut. These fragments can be made of dense, solidified rock, or they can be lightweight, frothy pumice or cinders during a powerful eruption. Lapilli can fall from the sky like a heavy, destructive hail, blanketing the landscape in a thick layer, often accumulating enough weight to collapse roofs. They are the middle children of the volcanic family, larger than the fine, dusty ash, but smaller than the dramatic volcanic bombs and blocks. The explosive power of a volcano is often thought to come from the magma itself, but one of the most powerful accelerants in its arsenal is simple, ordinary water. When magma comes into contact with external water, such as groundwater, a lake, a glacier, or the ocean, it can trigger an event called a phreatomagmatic eruption, or, if it's just superheated groundwater without new magma, a phreatic eruption. The thermal shock is extreme. The hot magma, which can be over 1000 degrees Celsius or 1800 degrees Fahrenheit, instantly flashes the water into steam. This phase change is incredibly violent, as water expands its volume by more than 1,700 times when it becomes steam. This sudden, massive expansion of volume is a blast of pure kinetic energy, a steam-driven explosion that shatters the magma and surrounding rock into fine particles and creates eruptions of extreme, devastating force, a true and primal battle between the elements of fire and water. Mount Rainier, the majestic snow-capped icon of Washington State, is considered one of the most dangerous volcanoes in the United States, but not primarily because of its potential for lava or ash. The greatest threat it poses lies in its immense and beautiful cloak of ice. Mount Rainier is the most heavily glaciated peak in the contiguous United States, holding a vast volume of water locked in its summit glaciers. The danger is that a future eruption, or even just a steam vent, or a landslide without an eruption, could rapidly melt this ice. This sudden release of water would mix with the loose, unstable rock and ash on the volcano's steep slopes, instantly mobilizing into a series of massive, fast-moving lahars, or volcanic mudflows. These concrete-like slurries would have little to stop them as they surge down the river valleys, traveling for dozens of miles at high speed, capable of reaching the populated lowland communities near Tacoma, a sleeping, icy threat held in check only by the mountain's current quiet. The birth of new volcanic islands, sterile and isolated in the vastness of the ocean, provides a perfect, living laboratory for the study of life itself. Islands like the Galapagos, Hawaii, and the newborn Circe are pristine, empty stages. Life's journey to these remote shores is a matter of pure chance, a desperate lottery of survival. The first arrivals are pioneers, carried by wind, wave, or wing. Tiny bacteria, fungal spores, plant seeds carried in the gut of a bird, or a spider drifting on a silk thread. Once they arrive, if they survive, they find a world of empty niches, free from the competition of their ancestral homes. This isolation and opportunity drive evolution at a rapid pace, a process known as adaptive radiation, as these few founders diversify into a wondrous array of new, unique species, like Darwin's finches, each one adapting to a different part of the new land. These islands are a testament to life's profound tenacity, its ability to find and flourish in the new worlds that the Earth's fire brings forth from the sea. The magma chambers that feed volcanoes are often pictured as vast, sloshing, underground caverns of molten rock, like an inverted lake of fire. However, decades of seismic research and geological study have revealed a far more complex and subtle reality. These chambers are not typically giant, open voids, but are more accurately described as crystal mush zones. They are vast, sponge-like regions in the Earth's crust, miles or kilometers wide, where a relatively small percentage of molten rock, the melt, exists in the tiny spaces between a much larger, semi-solid matrix of interlocking hot crystals. Over long periods, this melt can slowly separate from the crystal mush, accumulating in smaller, more liquid-rich lenses that are the true eruptible bodies of magma. This understanding has reshaped our vision of a volcano's plumbing, from a simple cavern to a complex, simmering, and slowly maturing crystalline heart, hidden deep within the crust. The 2018 eruption of Kilauea in Hawaii was a profound, landscape-altering event that fundamentally reshaped the volcano and its surrounding communities. After decades of relatively predictable activity at its summit, Lava Lake and the Pu'u'o'o vent, the volcano's plumbing system underwent a dramatic change. The magma drained from the summit, and instead, a series of fissures tore open in a residential area known as the Leilani Estates, far down on the volcano's lower East Rift zone. This event brought the volcano's power to an unprecedented, intimate level, as fountains of lava, some reaching hundreds of feet high, erupted in streets and backyards. The lava flows were vast and persistent, ultimately covering over 13 square miles, or 35 square kilometers of land, destroying over 700 homes and creating a massive new delta of land where the lava poured into the Pacific Ocean for months. A powerful and heartbreaking reminder that the entire island is a living, breathing, and ever-changing creation of the volcano itself. The city of Orvieto in Italy is a stunning example of human ingenuity. A city perched atop a high, steep-sided plateau of volcanic rock. This plateau is a tough plug, the solidified, hardened remnants of a massive pyroclastic flow from a nearby ancient volcano. While this high, sheer-walled position made the city incredibly defensible, it also created a profound problem: access to water. In 1527, a remarkable solution was commissioned: the Pozzo di San Patrizio, or St. Patrick's Well. This engineering marvel is not a well in the traditional sense, but an incredible 174-foot or 53-meter deep shaft dug straight down through the volcanic tuff to reach the water table. The well's true genius lies in its design: a double helix staircase with two separate one-way ramps spiraling around the central shaft, one for the mules to go down and one for them to come up, ensuring they never collided while carrying their heavy loads of water. This hidden, spiraling, subterranean architecture remains as a silent testament to the creative ways humanity is adapted to live within the landscapes that volcanoes provide. The Yellowstone caldera, the heart of Yellowstone National Park, is one of the largest supervolcanoes on Earth, and its ground is literally, measurably breathing. The vast magma chamber that lies miles beneath the surface is not a static pool, but a dynamic living system that is constantly being recharged with new magma from the mantle plume below, and is also releasing heat and gases. This restless activity causes the entire floor of the caldera, a region spanning dozens of miles, to slowly rise and fall in a measurable, cyclical pattern. In some years, the ground may swell upwards by several inches as the magma chamber inflates, only to subside or deflate in other years as the pressure wanes or hydrothermal fluids escape. This slow, immense, and silent breathing of the supervolcano, tracked by satellites and GPS, is the quietest, most patient heartbeat on the continent, a vital sign of the colossal power that sleeps just beneath the park's serene, beautiful surface. Iceland, the land of fire and ice, owes its very existence to a unique and potent geological combination. The island is not just a typical volcanic region. It is one of the few places on Earth where a mantle plume, or hotspot, is located directly on top of a mid-ocean ridge, the seam where the North American and Eurasian tectonic plates are actively pulling apart. This combination is a recipe for extraordinary volcanism. The spreading plates create a natural, persistent weakness in the Earth's crust, a rift that magma can easily exploit. The hotspot, meanwhile, provides a vast, buoyant, and abnormally large supply of magma, far more than at a typical ridge. This powerful, focused upwelling of molten rock, combined with the constant rifting, has built Iceland up from the seafloor, creating an island of such prolific and constant volcanic activity that it stands as one of the most geologically dynamic places on the entire planet, a true laboratory of creation. A black smoker is a type of hydrothermal vent found on the deep ocean floor, a place where the planet's internal heat meets the cold, dark abyss. These are, in essence, underwater geysers, chimneys of precipitated minerals that spew superheated water from the Earth's crust. They form at mid-ocean ridges where seawater percolates down through cracks in the new, hot volcanic rock. This water is heated by the proximity to magma to temperatures that can exceed 400 degrees Celsius or 750 degrees Fahrenheit, and it dissolves a rich cocktail of minerals from the rock, including sulfur, iron, zinc, and copper. This hot, acidic, mineral-rich fluid is then shot back up into the cold ocean. As it mixes with the near-freezing seawater, the dissolved minerals instantly precipitate or turn solid, creating a plume of smoke that is not smoke at all, but a dark, swirling cloud of fine, black mineral particles, which then build the chimney itself, a dark tower of life in a world without sun. A volcanic plug, also known as a volcanic neck, is the stark, beautiful skeleton of a volcano that has long since died and eroded away. These formations are created when viscous, sticky magma rises into the conduit or throat of an active volcano, but lacking the pressure to erupt, it slowly cools and solidifies within it. This process creates a massive, durable plug of hard, igneous rock, effectively corking the volcano over millions of years. The volcano itself, which is often built of softer, looser layers of ash and cinder, is worn away by the patient, persistent forces of wind, rain, and ice. This softer outer cone is stripped clean, leaving behind only the incredibly hard, erosion-resistant inner plug, which now stands alone on the landscape as a steep, solitary, an often dramatic tower, like Shiprock in New Mexico or the Devil's Tower in Wyoming, a silent monument to the fiery, beating heart of a mountain that is no more. The 1985 eruption of the Nevado del Ruiz volcano in Colombia was a tragedy that underscored a volcano's deadliest and perhaps most preventable hazard, the lahar. The eruption itself was not large. It was a relatively small explosive event that sent a pyroclastic flow cascading from the summit. The true disaster was that the volcano's summit was, and is, covered by a thick ice cap. The heat of this small eruption was enough to rapidly melt a portion of the glacier, unleashing a sudden, massive torrent of water. This water mixed with the volcanic ash on the mountain slopes, instantly mobilizing into a series of fast-moving, concrete-like mudflows. These lahars surged down the river valleys, traveling over 60 miles, or 100 kilometers from the volcano. They arrived in the town of Armero in the middle of the night, burying it in a deep, cold, grey tomb. A devastating lesson that a volcano's most lethal weapon is not always its fire, but its ability to mobilize its own history with water. The island of Japan is a nation born of and living in a constant, intimate dialogue with volcanic and tectonic power. The Japanese archipelago lies at the convergence of 4 major tectonic plates, including the subducting Pacific Plate, a geological setting that has created a landscape of intense dynamism. This has gifted the nation with over 100 active volcanoes, a constant source of geologic hazard, but also a deep and integral part of its culture. This volcanic nature has given Japan its hot springs, the onsen, which are a cherished central part of social and spiritual life, a place of purification and rest. It has given them Mount Fuji, the serene, symmetrical stratovolcano that is not just a mountain, but the nation's most sacred and recognizable symbol. The volcanoes are the Kanabi, the places where the gods, or kami, are believed to descend to earth, a constant, living, and revered presence that is both the creator and the challenger of the land. Xenoliths are foreign rocks, geological travelers that are captured and brought to the surface by rising magma. As magma begins its long, slow ascent from the deep mantle or a crustal chamber, it is not a pure, isolated liquid. It is a powerful, flowing, and sometimes forceful body. On its journey, it can rip or pluck solid fragments of the surrounding country rock through which it is passing. These captured pieces, the xenoliths, are then entrained in the molten flow, like an object trapped in amber. They are carried upwards, sometimes for dozens or hundreds of miles, and are often baked, melted, or chemically altered by the intense heat of their magma prison. When the volcano erupts, these xenoliths are ejected, frozen within the new solidified lava, offering geologists a rare, precious, and direct sample of the deep, hidden layers of the Earth's crust or mantle, a rock within a rock that tells a story of the deep, unseen world. A maar is a specific and beautiful type of volcanic landform, a low-profile, broad volcanic crater that is often filled with water to form a lake. Maars are not created by the eruption of lava, but by a series of violent, steam-driven explosions known as phreatomagmatic eruptions. This occurs when rising magma encounters a significant source of groundwater, an aquifer close to the surface. The intense heat of the magma flash boils the water into steam, creating a massive underground pressure bomb. This pressure builds until it finds release in a series. This erupts a massive, fast-moving, ground-hugging cloud of CO2, a gas heavier than air, which silently displaces the oxygen, leading to the tragic, silent suffocation of any living thing in its path, as seen at Lake Nyos in Cameroon in 1986, of powerful explosions that blast a deep, circular hole in the ground. These eruptions produce very little new magma or lava, but instead throw out a ring, or tough ring, of shattered, pulverized country rock, ash, and steam. Once the eruption ceases, the deep, steep-sided crater, blasted below the original ground level, fills with rainwater or groundwater, leaving behind a serene, almost perfectly circular lake, a peaceful and watery scar from a fiery, steam-powered birth. The Volcanic Explosivity Index, which measures the power of eruptions, is complemented by the Volcanic Ash Advisory Centers, or VAACS. This is a network of 9 centers, operating in different regions across the globe, established to deal with the specific and global threat of volcanic ash to aviation. Following the near disasters of the 1980s, when passenger jets lost engine power after flying into ash clouds, this system was created to monitor and track the movement of these airborne hazards. When a volcano erupts, the local VAAC, using satellite data, ground reports, and sophisticated atmospheric models, issues advisories to air traffic control and pilots. They forecast the ash cloud's trajectory, its altitude, and its density, allowing aviation authorities to close airspace and reroute flights in real time. This quiet, global network of scientists is a modern, technological expression of respect for the volcano, an invisible, planet-spanning web of communication designed to keep the air safe from the fine, sharp dust of the Earth's fire. The most common rock on the entire surface of the Earth, the very skin of our planet, is basalt. This dark, fine-grained volcanic rock is the fundamental building block of the world's ocean basins. It is the rock of the mid-ocean ridges, the material that is continuously and quietly erupting from the planet's great seams to form all new oceanic crust. It is also the rock of the Great Shield volcanoes, like those in Hawaii and Iceland, and the rock of the colossal flood basalt provinces, like the Deccan and Siberian traps. Its ubiquity is due to its simple origin. It is the direct first melt product of the Earth's upper mantle. When the mantle rock, peridotite, begins to partially melt, the liquid it produces is basaltic magma, a fluid, low silica melt that rises easily to the surface. It is the planet's primary, most basic, and most abundant expression of its own internal heat, the simple, dark stone that forms the foundation of our world. A solfatara is a specific type of fumarole, a volcanic vent whose breath has a unique and pungent chemical signature. The word itself comes from the Italian solfo, meaning sulfur, and these are vents that emit a gas mixture dominated by sulfurous compounds, particularly sulfur dioxide and hydrogen sulfide. As these hot, acidic gases escape and mix with the surrounding air and moisture, they react to deposit bright, beautiful, and often delicate yellow crystals of pure, native sulfur around the vent's opening, painting the ground in vibrant, otherworldly hues. The gases also aggressively attack the surrounding rock, breaking down the hard lava and ash into a soft, pale, and often clay-rich soil, a process known as argillic alteration. A field of solfataras, like the famous ones in the Phlegraean fields near Naples, is a landscape of both color and decay, a place where the Earth's chemical breath is actively, quietly unmaking and remaking the stone. The planet Venus, Earth's celestial neighbor, is a world that has been profoundly, and perhaps terrifyingly, shaped by volcanism. Its surface, shrouded in a thick, toxic atmosphere of carbon dioxide, is a landscape of volcanic features on a scale that is difficult to comprehend. Venus is home to more volcanoes than any other planet in our solar system, with over 1,600 major volcanic centers and perhaps 1 million smaller ones. Its vast plains are not ancient and cratered, but are relatively young, vast seas of solidified flood basalts. It features towering shield volcanoes, strange, steep-sided pancake domes formed by viscous lava, and unique spider-like fracture patterns called arachnoids. There is strong evidence that this volcanism is not just ancient history, but may still be active today, with recent data showing hotspots and sulfur dioxide spikes. Venus is a hothouse world, a portrait of a planet where the volcanic exhalation of gases, unchecked by oceans or life, led to a runaway greenhouse effect, a silent, sweltering monument to the fire within. The 17th century eruption of the Huaynaputina volcano in Peru in the year 1600 was the largest volcanic eruption in South America in recorded history. This was a colossal VEI 6 Plinian event, a cataclysm that ejected a vast quantity of ash and aerosols, not just locally, but globally. The eruption had a profound and documented impact on the world's climate, triggering a volcanic winter that was felt across the Northern Hemisphere. Historical records from Russia, for example, describe the Time of Troubles, a period of extreme cold and crop failure from 1601 to 1603, which led to a devastating famine, the worst in the country's history. This event is a powerful, well-documented example of the Earth's interconnectedness, a single explosive event in the Andes that reached across the planet to alter the climate, topple harvests, and rewrite the course of human history in lands that never even knew the volcano's name. The 1902 eruption of Mount Pelée on the French island of Martinique in the Caribbean was a tragedy that introduced the world to the nuée ardente, or pyroclastic flow. The volcano had been rumbling for weeks, but the island's authorities, concerned with an upcoming election, downplayed the danger and discouraged the evacuation of the vibrant coastal city of Saint-Pierre, which sat at the volcano's base. On the morning of May 8th, the volcano's lava dome collapsed or exploded, unleashing a superheated, fast-moving flow of gas and ash. This dense, heavy cloud did not go up, but instead raced down a valley directly towards the city at over 100 miles per hour, or 160 kilometers per hour. It was over 1,000 degrees Celsius, or 1,800 degrees Fahrenheit, and it annihilated the city in less than 2 minutes, instantly ending the lives of its nearly 30,000 residents. The event was a horrifying, definitive lesson in this particular volcanic hazard, and its only widely cited survivor was a prisoner, Ludger Silbaris, who was protected by the thick stone walls of his partially underground jail cell. The island of Iceland is a place where geology is not a static background, but a living, breathing, and visible force that shapes the land in real time. This is one of the few places on Earth where a mid-ocean ridge, the great seam where tectonic plates are born, rises above the surface of the sea. In places like the Thingvellir or Thingvellir Plain, you can literally walk or even scuba dive in the rift valley between two continents. On one side is the edge of the North American plate, and on the other, the edge of the Eurasian plate, and the ground between them is a landscape of fissures, cracks, and canyons known as jar. This is the land that is actively being torn apart, stretching by about an inch or a couple of centimeters every year as the plates move away from each other. It is a quiet, steady, and relentless process, a place where you can stand and physically touch the edges of two worlds. A silent, profound testament to the planet's constant, patient, and creative motion. The island of Hawaii, the Big Island, is a unique and magnificent geological entity, as it is composed of 5 great shield volcanoes that have grown together to form a single landmass. These 5 mountains, each a giant in its own right, are Kohala, the oldest and extinct; Mauna Kea, which is dormant; Hualalai, also dormant, but still considered active; and the 2 most famously active, Mauna Loa and Kilauea. These volcanoes did not all form at once, but were born sequentially as the Pacific Plate drifted over the Hawaiian hotspot. The island is a living, growing, and breathing portrait of the volcanic life cycle. In the northwest, you see the old, eroded, and quiet mountains, their fires long extinguished. In the southeast, you have the youthful, hyperactive, and constantly growing Kilauea, which is currently building new land. The Big Island is not just an island. It is a family of giants, a single place where you can see the past, present, and future of the Earth's creative, fiery, and patient power.
And so, our journey through the majestic world of volcanoes comes to a gentle close.
We have drifted from the deep ocean floor, where silent giants like Tamu Massive sleep, to the icy plains of Antarctica and the tormented fiery surface of Io. We have seen how the Earth breathes, its fiery exhalations creating new lands like Surtsey, and how it recycles its own skin. At the great mid-ocean ridges, we have listened to the different voices of the fire, from the steady, rhythmic heartbeat of Stromboli to the sudden, violent roar of a Plinian eruption, and we have learned to read the quiet warnings in the swelling ground and the chemical whispers of a fumarole. These mountains are the planet's sculptors, the givers of fertile soil, and the masters of sudden, profound change. They are the forge of Vulcan, the home of Pele, and the silent, geological heart of our world, reminding us that the ground beneath our feet is not a static, finished thing, but a living, breathing, and ever-evolving surface. The stories of stone and fire are now settling into the quiet of the night, their immense, slow power fading into the soft background of your rest. If you happen to still be awake, that's perfectly all right. You can simply lie back, let the music keep flowing in the background, and drift in and out of the story at your own pace. But if your eyes are heavy, let the stories of volcanoes and the gentle music carry you softly into rest. Sleep well. Good night.